Hello, grade 11s. Welcome back to the channel. In today's lesson, we're going to be looking at acids and bases. And without any further ado, let's look at this question 7 that we have here. It says phosphoric acid, which is H3PO4. And looking at this, we can see this is a triprotic acid. And we can see it undergoes 3 steps here to give away all its 3 protons, which reacts with water through the following 3-step reaction as told here. And then we can see that in the first step, it's giving away 1 proton and then giving it away to H2O here, water. So this is an acid and the water acts as a base. That means the acid goes to its conjugate base here, which is H2PO4 minus. And then this base here will go to its conjugate acid, which is H3O plus, which we know it as the hydronium ion. Now, according to Arrhenius, we know that this is an acid because it produces hydronium ions when reacted with water. So if we react a substance with water and it produces hydronium ions, we know that it's an acid. So this is all acids in here, and these are all bases in here, right? And then what we have here is the conjugate base, and then here the conjugate acid. So base acid. Now 7.1.1 says, why is H3PO4 a Lowry-Brønsted acid? Now we know that the solution to this one, why is H3PO4 a Lowry-Brønsted acid? We have to ask ourselves first, what is a Lowry-Brønsted acid? We say that a Lowry-Brønsted acid is a substance or an acid that donates a proton, right? So it's a substance that donates a proton. So we say it's because it's a proton donor, right? H3PO4 is a Lowry-Brønsted acid because it donates a proton. It donates a proton. Or you can simply say it's a proton donor. Okay, then you have your 2 marks like that. 7.1.4 says define the term ampholyte. We know what an ampholyte is. We say this is a substance. This is a substance that can act as either an acid or a base. An acid or a base, right? So that's your ampholyte. And then in 7.1.3 says identify 2 substances that act as ampholytes in the reactions above. Now remember, an ampholyte has to act as an acid in one reaction and act as a base in another reaction. So looking at this, we can see that as much as we know that water acts as an ampholyte in most of the cases, but in this case here, it is not an ampholyte because in all these reactions, it acts as a base. Can you see that? So this one cannot be an ampholyte because in all these cases, it acts as a base. Also, your H3O plus cannot be an ampholyte because in all these cases, it acts as an acid, right? So what must be the ampholyte in this case? Remember, here we have a base. So looking at this substance here, we can see that this substance in step 1 or reaction 1, it acts as a base. But then in step number 2, it acts as an acid, right? So we can say that this is the same substance, but in reaction 1, it acts as a base, and in reaction 2, it acts as an acid. Again, so the first one that we have is H2PO4 minus, and again here, look at this one, HPO42 minus. In this reaction here, in step number 2, it acts as a base, but then in step number 3, this reaction here, we can see that it acts as an acid, right? So in this case, we will say both these substances are ampholytes. So you have your 2 marks again. Then 7.1.4 says write down 1 conjugate acid base pair for step 2. Now already we have seen this. This is an acid. This acid will go with its conjugate base here. So to write the conjugate base, we simply say the pair of conjugate base can be H2PO4 minus 2 H PO4 2 minus, or the other one that you have is H2O 2H3O plus, right? So these are your acid base pairs, right? So you simply take the acid from here and you direct it to its conjugate base, and you take the base in here, you direct it to its conjugate acid. So that's how you find the conjugate acid base pairs. Then 7.2 says complete and balance the following reactions. So we have 7.2.1. This one, we can see that this is an acid, a weak acid for that matter. And then we have NaOH, which is sodium hydroxide, a strong base, right? So in this case, we know that this one will give away the H because remember, it's an acid. And then in giving away the hydrogen proton, then what will come in here to close off that gap is your sodium ion. And then since you'll be left with OH here, the hydroxide ion, the H that will come from here will react with the OH, and then you'll have water, right? So in this form, you have your balanced equation. Then for this one, this is HCl reacting with calcium, with calcium carbonate. So we know with this one, when we have the carbonates reacting with hydrochloric acid here, we know that will form a salt and carbon dioxide and then water, right? So in this case, this must break down to Ca, Cl2, and then now we will form our H2O, and then we also form our carbon dioxide. So it's always like this. This reaction will always produce water and carbon dioxide and a salt here. So we have calcium chloride plus H2O plus carbon dioxide. Now, is this all balanced? It's just a matter of checking if this is balanced. Now we can see that we have 2 chlorine atoms here. So in order to balance the chlorine atoms, we need to put 2 in front of this one here. Then we have 2 chlorine atoms and 2 hydrogen atoms, which even from here, we have 2 hydrogens atom from the H2O. So this is now balanced. So you have your 3 marks like that. Okay, now let's move to another question. We have question 7. It says a sample of chalk containing 95% calcium carbonate, which we are given the molecular formula there, was reacted with excess dilute hydrochloric acid and 2.128 dm cube of carbon dioxide. So we can see that the 2.128 dm cube is of carbon dioxide and was collected at STP. The minute we see this keyword STP, we now know that the formula that we have to apply here is N is equals to V over Vm, right? Then we are given the following balanced equation. So there will be no need for us to balance this. It's already balanced for us. Then that's calcium carbonate with hydrochloric acid. Now, look at this. Isn't it funny that we just balanced that one here in the previous question? Look, this is the same reaction. This is exactly the same reaction, right? So now always note that the calcium carbonate, when it reacts with hydrochloric acid, these are the products that will form, right? Then 7.1 says define an acid according to Arrhenius theory. Now always check. This one wants us to define according to Arrhenius theory. So according to Arrhenius theory, we say an acid is a substance. An acid is a substance that produces hydronium ions, right? So hydronium ions, which is your H3O plus in water, right? In water. So this is your definition of an acid according to Arrhenius theory. Then they say here, why is HCl considered a strong acid? So why is hydrochloric acid considered a strong acid? Whenever we give an answer to this one, we simply say, what is a strong acid? we know that a strong acid is an acid that ionizes completely in water. So why is HCl considered a strong acid? We simply say it's because it ionizes completely in water. So it ionizes completely in water. So that's it. Now they say write down the ionization of HCl in water. So we simply do this to show the ionization of HCl in water. So you simply say HCl reacting with H2O. This will give us, remember, according to Arrhenius theory, if this hydrochloric acid is reacting with water, this is an acid. It must do what? It must donate the proton. So if it donates the proton, we are only left with the chlorine ion there. So Cl minus, and then here we have H3O plus. So this one is already balanced. There will be no need to balance it. So it's balanced like this. This is the ionization reaction of HCl in water. So it ionizes to Cl minus and H3O plus, right? So that's how you show it. Now 7.4 says, calculate the mass of the sample of chalk used. Calculate the mass of the sample of chalk used, and that is for 3 marks. It's for 6 marks, meant to say. So now, how are we going to calculate that one? Look, we are given the balanced equation, and then what we are just given here, remember, the 2.128 dm cube was for carbon dioxide. Remember, carbon dioxide is the only gas here, and then it makes sense that it was collected at STP because this only applies to gases. So again, let's remind ourselves STP so that we do this one. Now, remember, this is a stoichiometric question, so you do not have to dadazel. So step one, we still remember, is to calculate the number of moles. Calculate the number of moles. So using which formula here, obviously the N is equals to V over Vm, right? And then we have the V was given to us as 2.128, then divide that by 22.4, right? So we have 22.4, and then let's have our calculators close by. So punch that in your calculator. We have 2.128 divided by 22.4. This will give us a value of 0.095 mole, right? But then step number 2, let's go back and read the question. What are we looking for here? We are looking for the mass of sample of chalk used, right? So they just told us that 95% of this chalk was calcium carbonate. So we do not have the formula for the chalk, but we do have the formula for calcium carbonate. So we can make use of that. But remember, the mass that we are going to find from here will only be representing 95% of the chalk, because remember, the calcium carbonate is representing 90% of the chalk, as we can read here, a sample of chalk containing 95% calcium carbonate, right? A sample of chalk containing 95% calcium carbonate. So from that statement, we can get that this calcium carbonate is representing 95% of the chalk, right? Okay, now that we are through with that, we have 0.095 mole, but this is of carbon dioxide, right? Now, what are we looking for? We are looking for calcium carbonate. So we'll say the ratio of carbon dioxide to the ratio of calcium carbonate is 1:1, right? As per our balanced equation here. So the coefficient is 1 here, and the coefficient is 1 here, right? So looking at this, it means that if I have 0.095 here, also the number of moles for calcium carbonate is 0.095. Remember, same ratio, same number of moles, right? So that will count as your step number 2, which is to use ratio coefficients. So use ratio coefficients, right? So you always know that in answering those questions 6, we use the stoichiometric steps, right? Then we have this. Now, what are we looking for? The mass, right? So we are looking for the mass of calcium carbonate. So to calculate that, we'll say N is equals to M over big M. So we have the 0.095, and then is equals to M. Calcium carbonate, by now you should know that the molar mass is 100, because it always appears a lot. So times 100, then M is 9.5 gram, right? So we have 9.5 gram, but then remember, this is only representing 95% of the chalk, right? So now we want the mass of the chalk. So to find the mass of the chalk, which is the 100%, we will simply say, so even if we use the percentage purity formula to say it's the mass of the pure over the mass of impure multiplied by 100. So we'll say we've been given the percentage, which is 95, and then here the mass of the pure we have calculated to be 9.5, but we don't have the mass of the impure, which represents the chalk, then times 100. So at this point, we can see that we can just simply say 9.5 multiplied by 100 over 95, right? So this will give us a total of, punch that in your calculator, this would be 10 gram, right? So this is the mass of the chalk. This is the mass of the chalk. And just like that, voila, you have your 6 marks. Then 7.5 says, the excess hydrochloric acid is neutralized by adding sodium carbonate. Write a balanced equation for the reaction between hydrochloric acid and sodium carbonate, right? Between hydrochloric acid and sodium carbonate. Now let's do that one. So let me just erase something. I want to write it down here so that you see what will actually take place here. So this is Na. This will be sodium carbonate is Na2CO3, right? So that's the formula for sodium carbonate. And then this must react with what? With hydrochloric acid. Now, this is still the same thing. If you react with a carbonate here, you are supposed to have H2O and then carbon dioxide forming here. And then here you are supposed to have a salt. Then this is what will form from here. This is sodium chloride. So sodium chloride, that's the salt that will form. Then plus, at this point now you want to balance. So you can see that we have 2 sodium atoms. And then to make it 2 here, we'll just balance by putting 2 here. But then now we have 2 chlorine atoms. So to balance that one off, we need to put 2 in front of HCl. Then we have 2 chlorine, and then also here 2 chlorine. But then now we have 2 hydrogens. Let's look. We have 2 hydrogens, right? And then how many oxygens? This is 1 plus 2. That's 3. And then how many oxygens this side? We have 3. Obviously, when it comes to the carbon, we have 1, and we also have 1 here. So everything is balanced, right? So you can see everything is balanced, and that's your 7.5. So as long as you know that when this reacts with a hydrochloric acid there, it forms H2O and carbon dioxide, then it's just a matter of producing the salt here. But then it's easier because if you have carbon dioxide here, and then you know that you have H2O, then it's just a matter of reacting the ones that are left here. So your Na and your Cl, they form that salt, right? So it should be quite understandable. Then we have now a very long question. So question 8, so these ones you can see that now they're different. If they now give you this question 8, this is where now you find your acids and bases being around 20 marks there. So the ones we've been doing, they've been around 14, 15. That's when they just give you basic acids and bases. Basic acids and bases. Sorry for the pun. Then 8.1 says, consider the balanced equation for the reaction of water with nitric acid and ammonia. So we know the nitric acid is this one and the ammonia is that one, right? So, okay, so we are given two reactions here. Both of these reactions are with water. And then as we can see here, the nitric acid is an acid, as it says. Then here, this one obviously acts as a base. But the ammonia, remember, it's a base. So the water here acts as an acid, right? So at this point, you can see that the water is acting as an ampholyte because in reaction 1, it's a base. And in reaction 2, it's an acid, right? So here, we can see that the nitric acid is an acid because it produces hydronium ions, and the NH3 is a base because it produces hydroxide, right? So hydronium ions if it's an acid, but hydroxide ions if it's a base, right? 8.1.1 says, define an acid in terms of the Lowry-Brønsted theory. So what is an acid? We say an acid is a proton donor. So that's how you define, according to Lowry-Brønsted, an acid is a proton donor, right? And then 8.1.2 says, write down the formula of one conjugate acid-base pair in reaction 1. So we know that in reaction 1, this acid will go with its conjugate base here, or this base here will go with its conjugate, no. Let's see. So this acid goes with that. Let's fix that one. So this acid here goes with its conjugate base over there, right? So remember HNO3, when it gives away the hydrogen, now it is left as NO3 minus. And then this base here will go to its conjugate acid here, right? So it's just close by. It's just close by. Okay, here. Nice one. So now they say write down what the formula of one conjugate acid base pair in reaction 1. So we'll say that's HNO3 to NO3 minus, or you can write the other one, which is H2O to H3O plus, right? So either one of this, remember they said only one conjugate acid base pair. So either one of this. And then 8.1.3 says, is the solution formed in reaction 1 acidic or basic or alkaline? So basic is just another way. Alkaline is just another way to say basic. Then give a reason for the answer. Now, this question is based only on checking which ion is produced. Is it the hydronium ion or is it the hydroxide ion? Now, if we produce hydronium ions, that means the solution is acidic. If we produce hydroxide ions, it means the solution is basic or alkaline, right? So in this case, in reaction 1, what is it that we have? We have, we can see here, hydronium ions. So that means it is what? Acidic, right? So it has to be acidic. And what's your reason for that? You simply say it produces hydronium ions. So you can even write it produces H3O plus like that. Then 8.1.4 says define the term ampholyte. So we are defining this for the second time right now. So what is an ampholyte? We say this is a substance. So be like me, guys. Don't be lazy to write the definitions over and over again. That's how you make sure that you remember them. A substance that acts as either an acid or a base. So it's a substance that can act as either an acid or a base. Then 8.1.5, write down the formula of a substance that acts as an ampholyte in the reaction above. Now, we've already discussed that. We can see that the water in reaction 1 acts as a base. In reaction 2, it acts as an acid. So it is definitely H2O. Now, they're saying, explain the answer by referring to the role of the substance in reaction 1 and reaction 2. So again, the reason is what we just gave here. we will say that in reaction one, it acts as a base. It acts as a base. Then, but in reaction two, okay, let me just write it here. Let me write it this side. So we'll say in reaction one, it acts as a base, but in reaction two, it acts as an acid. So that's it. That's the reason. And yeah. So we have explained 8.1.6. Then 8.1.7 says calculate the volume of water that must be added to the 0.2 mole dm cube of nitric acid. So we haven't read the statement here. So it says 100 centimeter cube, which we know conversion must take place because it's in centimeter cube, of nitric acid of a concentration of 0.2 mole per dm cube is diluted to 0.16 mole per dm cube. So from 0.2, it's now diluted to 0.16 mole per dm cube. Now this says calculate the volume of water that must be added to the 0.2 mole of nitric acid, right? So we already know this is the case. This is the case of moving from C1 V1 is equals to C2 V2, right? So whenever we have whenever we are told that we are moving from a certain concentration to a new concentration, then we know that we have to apply our formula C1V1 is equals to C2V2. So this is the concentration and volume before, and then this is the concentration and volume after, right? So reading the statement, we can see that we had 100 centimeter cube of nitric acid of a concentration of 0.2, and then now it is diluted, right? It is diluted. That means they now add water, right? So this is the case whereby I always say that if you have let's say your squash, your oros squash, then this is the volume before. So let's say maybe you have 50 centimeter cube of your oros squash, or let's put it in layman's term. Let's say you have 0.5 liters, right? 0.5 liters of this. Then you decide to put in water. Let's say you put 1 liter water, right? So remember you had 0.5 squash, and then now you are filling in water 1 liter. So the new volume in this case would be 1.5 liter, right? But then if here your concentration of the squash was maybe, let's say maybe 1.5 mole per dm cube. Now, if you dilute it, we know that the concentration will obviously decrease. Let's say maybe it decreases to 0.025 mole per dm cube. So basically, this is what is happening. So from a particular volume, when you dilute, when you add in water, remember to dilute is when now you add in water to that substance. Then now the volume will increase, but then what happens to the concentration? It will decrease, right? That's the case that is happening in here. Now let's check. We had our initial concentration is 0.2, right? So our initial concentration was 0.2. Then our initial volume was 100 centimeter cube, which we need to divide by 1,000. So 100 divided by 1,000, that's 0.1 dm cube. So that's our initial volume. So we have 0.1. And then what is it that we are looking for? We are calculating the volume, right? So now from 0.2, this decreased to a concentration of 0.16. So that's a decrease, right? Remember 0.20 to 0.16, that's a decrease of 0.04. Then V2 here, at this point, we can just divide both sides by 0.16. then you simply punch it in your calculator. Then that's 0.2 times 0.1 divided by 0.16. 2 is 0.125 dm cube, right? Of which, if you're interested in finding it in terms of centimeter cube, you can simply take the 0.12, multiply it again by 1,000, and then this in centimeter cube will give you 125 centimeter cube. So in that way, you can see that it increased from 100 centimeter cube to 125 centimeter cube. At this point, you can see that they added 25 centimeter cube of water. So they diluted with 25 centimeter cube of water. Then, okay. And that's how you get your 4 marks, guys. Let's proceed. We have 8.2 says zinc oxide, which is ZnO, is insoluble in water. That means it does not dissolve in water and can be harmful to the environment. Nitric acid can be used to neutralize zinc oxide. So luckily now we know that zinc oxide is insoluble in water, does not dissolve in water, but then now luckily we have the nitric acid to neutralize that. Then they say the incomplete equation for the reaction is given here, right? So we are given this, and then 8.2.1, so the mass of zinc that can be neutralized by 80 centimeter cube of nitric acid with a concentration of 0.16 mole per dm cube. And that is for 5 marks, right? So we know very well that when we have this, this is still stoichiometry, right? Because let's check, we are given the volume, and then we are given here the concentration. So we can start by calculating the number of moles, right? So, okay. So I was still trying to check if this question has any link with the previous question that we just solved. And then, unfortunately, it doesn't. So this one is a different question with its own statement. So it's not, it's 8.2. So it does not link with 8.1.7. Okay, so now let's solve. We have the balanced equation here, or rather an incomplete equation. So we cannot say it's balanced because it's incomplete. But then we are not concerned about salt X at this moment. We just want to calculate here. So what are we given? All this that we are given here is applies to the nitric acid. But then what are we trying to calculate? The zinc oxide, right? So at this point, we still apply our stoichiometric steps, which is step 1 is to calculate the number of moles. So step 1, so calculate number of moles. And then this will be, from what we are given, the formula that we're going to apply, C is equals to N over V. And then the C is 0.16. 0.16. So we can see this is the concentration, the new concentration that it got from that question. Then N, then the V here is 80 centimeter cube, but we know exactly that when it's in centimeter cube, we need to divide by 1,000. So you take that 80, divide by 1,000, and then it will give you 0.08. So we have 0.08 here. And then when we cross multiply, this should give us 0.08 times 0.16. That should give us 0.0128. So the number of moles is 0.0128 and then mole, right? But then we know we are not looking for nitric acid. We are looking for zinc oxide. So at this point, step number 2 is to use ratio coefficients. So use ratio coefficients. So by saying the ratio of nitric acid to the ratio of zinc oxide, that's 2 is to 1, as we can see from here. And then The number of moles for nitric acid is 0.0128. So we have X here. If we cross multiply, this is 2X equal to 0.0128. Then we can divide both sides by 2. So the X becomes that divided by 2. So it's 6.4 times 10 to the exponent of -3 mole, right? So we have our number of moles like that. Now, what is it that we are looking for? We are looking for the mass. So we should not be carried away in the question. So we are still looking for the mass. So that's N is equals to M over big M. So that's 6.4 times 10 to the exponent of -3, and then M over the molar mass of zinc oxide. Now we have to consult our periodic table for that. So what is the molar mass of zinc? It's something, is it 65? Yes. So we have 65 plus 16. So that gives us 81. So 81. When we cross multiply 81 and all of that, so what is it that we get? It's a mass of 0.52 gram, right? So that's a mass of 0.52 gram. And just like that, you have your 5 marks. Okay, then 8.2.2 says, write down the name and formula of salt X that forms during this reaction. So what salt forms during this reaction? You can see that we just produced water here, H2O, and then we know exactly that we should form the salt here from whatever that's left. So from here, we can see that the H2O will obviously form from these 2 hydrogen atoms here and the oxygen here. So what is left of is the zinc and the nitrate. So at this point, we can see that our salt will be zinc nitrate, right? So that's zinc NO3, but then 2 here, right? So that's zinc nitrate. So that's zinc nitrate. If you want to write the name, because they said name of formula. Name and formula. So name and formula. So that's zinc nitrate.